Hello and a warm welcome back to my YouTube channel. This is iGCSE Chemistry and we're going to today have a look at electrolysis. So lysis means splitting up, breaking apart. Electro, no prizes for guessing. It is electricity, so it's using electricity to split stuff up. And the stuff is, don't use that. Stuff is ionic solids. Now, ionic solids are, well, let's have a quick define ionic bonding. That's a great place to begin. So it is the attraction in between oppositely charged ions. Now I know this is iGCSE, so you could say metal with a non-metal, which is true. Nothing wrong with that. You do have to know, however, that the metal would be positively charged and the non-metal would be negatively charged. And non-metal could be N, and this could be X. One or more could be the charge on those things. So why not covalent? Why not covalent? Why can covalent molecules not be electrolyzed? Well, electrolysis is to do with splitting up. And we have a negative electrode and a positive electrode. The long stick is positive, because if we take that long stick, split it in half, and lay it over each other, it's positive. So that's going to be the anode. Jolly good. You got that right. There we go. Anode. Fantastic. So the negative, hate cats, want to kill cats. Cathode, dead cats, red cats, dead ginger cats. Because reduction happens at the cathode, but we'll come to that in a little while. The question was, why not covalent? Well, covalent molecules are things like CO2 and H2O and carbon as graphite and carbon as diamond. I'd love to get some diamond electrodes, sell them, and go for a fantastic holiday, but that's not going to happen. Why can these not be electrolyzed? Because there is no charge separation. Basically, there is no negative or positive ions to carry the electricity. So in a multiple choice situation, and it gave you a list, if it is two non-metals, so right hand side of the periodic table, so here's your periodic table, bish bash bosh, all the stuff that's over here, these are the non-metals. These will never be able to be electrolyzed. But if you're bonding any of these, and probably some of these, and definitely some of those, with some of these, and some of the halogens just there, then bish bash bosh, you have separation of charge and you can perform the wonder that is electrolysis. So there is a caveat to this. Yes, only ionic compounds are capable of being electrolyzed, but the ionic compounds must be in a specific state. So NaClG, and I'm missing one, aren't I? Which one is it? You got it, L. So, can solid sodium chloride be electrolyzed? Is it electrolyzable? I'm not sure that word exists. If it doesn't, it does now. So, this is plus and minus and plus and minus. And this goes off in three dimensions in an array of oppositely charged ions. And these are fixed. So the ions are fixed. They cannot move. So can this be electrolyzed? No. They will sit there, look at you, and nothing will happen. If we put it into aqueous solution, well, these ions, these pluses and these minuses, now they are free to move. Free, let's put loads of E's there. Free to move. So they can move, so this can be electrolyzed because the ions, make sure you get this right, the ions, not the electrons, the ions are free to move. So if it is ionic, which sodium chloride is an obvious example, then you can electrolyze it if it is aqueous or liquid. We'll come to gas in a second, that's an interesting one. If it's liquid, sodium chloride. Now this is not what you normally experience in everyday life. You don't normally get the table salt from the table. Instead of putting it into your soup or on your chips or on your gyoza, you don't go, oh my gosh, I'm going to put this in a flame and see what happens when I melt it. If you melt sodium chloride, it has a very high melting point. I think it's somewhere around 800 degrees C. You can almost get there with a Bunsen burner, depending on the gas mix. Some do get there. And you'll find videos on YouTube. Have a look. So NaCl in H2O, but it has to be liquid. And as soon as it hits the H2O, it's really hot, it explodes and smashes fish tanks apart and stuff like that. So that's all giggles. But this one, are the ions free to move when it's liquid? Well, yes. The kinetic model says that this is free movement around the container in which it is sat. So the ions are free to move. Okay? So if the ions are free to move, then you can electrolyze your ionic compounds, but you cannot electrolyze a covalent compound. Gaseous NaCl, I'm obviously freestyling, and I never really thought about that. If you gasify it, if you made it into its gaseous state, I suppose it depends how far away the ions were. Could you electrolyze it? I doubt it very much. Maybe you condensed it, but if you condensed it, it would become a liquid. So I'm going to say no. I'm sure some clever person's going to say, well, if the ions were close together, the answer is no. It's not any mark scheme. Only liquid and aqueous are capable of being electrolyzed. So, what do we need to have? We must have an ionic. Go away. We must have ionic. If it's ionic, this is our check sheet. Is it ionic? Yes. Happy faces. Tick. Is it molten? That means melted, liquid. Yes. Happy face. Brilliant. Is it solid? Yes. Well, unhappy face. Cannot. Is it aqueous or dissolved in water? Yes. Can. Why are we able to electrolyze it in those situations? It's because the ions are free to move. And it is the ions, not the electrons, the ions in which two states? Molten and aqueous. Must be ionic, molten, and aqueous. Aqueous, ionic, molten, molten, ionic, aqueous. Get that in your head. Brilliant. Moving on. So, in electrolytic cell, let's draw one out. An electrolytic cell. So what colour should we use? Let's use purple. Purple's a great colour. Okay. So I'm going to draw my bucket. Sorry, my beaker. Here's a beaker. And I'm going to put into here an ionic solid. No, solid doesn't like this dimension. We cannot use that. So let's use a molten ionic compound. And let's use one that's on your syllabus. Your syllabus actually says this for 0654. I'm going to use lead bromide. Okay, so I'm going to take some lead bromide, get a Tina Turner Bunsen burner, stick it underneath, give it some heat. We're going to heat it up, we're going to melt it. We're chemists, even melting a liquid ionic solid to make it a molten ionic compound is not enough. We also then go and stick some electricity through it, put a potential difference or throw some current through the molten ionic salt. Remember the little and the big? Didn't mean to do that. That's better. The little one is the negative, and the long one is the positive. Because if you take the long one and split it into two, it becomes two little ones and makes a plus. And I'm negative. I hate cats. Kill cats. Dead red cats. Dead ginger cats. Negative cathode and the positive anode. Okay, so we can label these. So this is the anode. This is the cathode. We care about that. The thing that sticks into this is the electrolyte. And these two are the electrodes. Anything else we're missing? We've got heat, we've got electrolytes, we've got a beaker, we've got a power supply. The electrodes, these are the things that stick in the electrolytes. They can be inert or active. Inert means just don't get involved. It's far too posh to deal with the likes of you. Do not get involved. Okay? They don't participate. Active electrodes do. We might come to that today, but that's to do with copper electrodes, and we'll come to that perhaps later. So what do we have? Well, we have an electrolytic cell. We have a desire to pass our iGCSE in Coordinated Science Chemistry. So if I'm going to stick an electric current through PBBr2, I need to understand that bromine is from group 7, and that means it's a halogen. And all halogens have a charge of -1. So this little 2 here means there's 2 times -1. If this is 2 times -1, which is -2, then for this to be 0 overall, the lead bromide is 0, -2 add x equals 0, therefore x equals +2. So the charge on this is +2. That's useful because in our little cell, let's do a little quick drawing here, bish bash bosh. We're going to have lead 2+, and opposites attract, right? Opposites attract, they always have, they always do, and they always will. So opposites attract. And the negative, the one that I hate and really negative about cats, it's the cathode, the negative cathode. So the cathode is negative. So lead will be attracted to the cathode. And what will we get? We'll actually see some lead, some solid lead. Okay, so this is liquid. Now what we need to think is, well, on this side, there is 0 charge. It's just a neutral lead atom. But on this side, there's lead with a 2. It's ionized. It's the preferred oxidation state, or the preferred charge on lead. How do we balance this? We use electrons. Let's add 2 electrons, because it's got 2+. So +2 -2 equals 0. That's 0, so the charge is balanced. Beautiful. Lead 2+ has gained 2 electrons. Don't forget your oil rig. Okay, so oxidation is loss and reduction is gain. Oxidation is loss, oil, reduction is gain. Rig of electrons. Not of pomegranates or mangoes or guava or mangosteen or any of those things. It's of electrons. So what has happened here? Well, we've got lead 2+, write it out one more time, +2 electrons goes to lead. This has gained electrons. Oxidation is gain, oxidation is loss, reduction is gain. So this has reduced. This is a reduction. Reduction is gain of electrons. Anything on the left-hand side is gain. Anything on the right-hand side of this arrow, and our students sometimes get confused with this, the arrow dictates whether this is left or right. This is to the left, this is to the right, and then LH side is gain, and then the right-hand side is loss. Okay, so we've got our lead, we've got our reduction. You can't have reduction without oxidation. So you can't have reduction without oxidation. So what's the oxidation? We've also got Br-, because it's PBBr2, is our Br. It's 2 times -1. So bromide the ion is going to be floating around. Don't forget the ions need to be free to move. They're free to move because it's molten, melted. Br minus is going to make bromine. Now, it's little facts that you need to know, but all the halogens are, posh term is diatomic molecules, but there are 2 atoms per molecule for every halogen. Now, there are 2 Br atoms on this side, but there's only 1 here, so I need to add 2 there. I know that the lead was reduced here. Lead 2+ was reduced, picked up 2 electrons from the circuit and deposited lead metal. 2 Br minus here, so that's 2 minus charge on this side, 0 charge on this side. In the same way, exactly the same way as the reduction, this is going to be the oxidation. So instead of electrons on the left, the electrons are going to be on the right. These 2 electrons here and these 2 electrons there are the same electrons. What does that mean? Well, that means that these 2 that are picked up here are the same 2 that are given off there, because you can't have reduction without the oxidation. That means I can put them together. So I'm going to put a line down. I'm going to add everything on this side. So Pb2 plus 2Br minus, that's this one and that one, is going to go to Pb plus Br2. And that is the full redox equation. 2, 2, 1, 1, plus 2 minus 2 is 0, 0 plus 0 is 0. Bish, bash, bosh, give me 6 marks. Yay! So that's electrolysis of any molten salts. I'll do one more with you before we go on to aqueous salts. So let's have molten, let's have copper. What do we have last time? We had bromide. So let's have copper chloride. Okay, so draw the cell. I hope you're doing this at the same time as me. Draw the cell. Little one, cats, want to kill cats, hate cats, that's the cathode. That means that's the anode. I'm going to have the electrodes. These 2 are the electrodes. These are inert, they don't get involved. That means they could be made of carbon, or if you're rich, they could be made of platinum. This is the electrolyte. So this is where the ions are free to move. Okay. We've got copper, we've got chlorine. Halogens always have a -1 charge. Halogens always have a -1 charge. Thank you. That means there are 2 times -1, which is -2 for the chlorine. That means this must be +2. Right, thank you. So we're going to have a reduction and we're going to have an oxidation. What will be the equations? The metal always reduces. The metal always reduces. So copper 2+, let's do that in a second, will deposit copper. So you'll see this electrode, negative electrode, hate cats, want to kill cats, growing with a red metal because it's picking up 2 electrons at the cathode and depositing copper solid. The reduction, we're going a bit quicker now because I went through the last one very slowly. Cl-, halogens are always 1-, and halogens always exist as diatomic, or 2 atoms per molecule. So there's 2 chlorines here, we need 2 chlorines there, and we need to lose 2 electrons on the right hand side. These 2 will cancel out, so we can do the overall equation, which is copper 2+ plus 2Cl- goes to Cu plus Cl2. Beautiful. Right, so that's 2 ionic solids that have been melted. So 2 molten ionic solids. Okay, the other ones mentioned in your syllabus, 0654 Coordinated Science, are dilute H2SO4 and concentrated NaCl, aqueous. We'll come back to those after we've had a quick look at, we said we could electrolyze molten. We said we could also electrolyze aqueous ionic salts. So if you have an ionic salt and it's been dissolved in water, you can put electricity through it and you can get a variety of products. So we just did copper chloride up here, and we got copper and we got chlorine as products. That was when it was molten. Now let's put copper chloride as an aqueous solution. And as soon as you see aqueous, you're then thinking, not only do I have copper 2 plus and Cl minus, let's make that neater. We have copper 2 plus and Cl minus. We also have water, and water will dissociate into H plus and O2 minus. You can also say OH minus. Okay, so now we're going to have competition, because at the cathode, hate cats want to kill cats, dead red cats, we have reduction at the cathode. Still, by definition, we have reduction at the cathode. Reduction is the gain of electrons, oil rig. Oxidation is loss, reduction is gain. So that means the thing that will be attracted to the negative cathode will be anything that's positively charged. So it could be copper 2 plus or H plus. Either of those could be attracted to the cathode. And then the oxidation at the anode, you got it, either O2 minus or Cl minus will be attracted to the positive anode. So let's have a look at balancing up. It's good practice for us. So Cu2 plus is going to make, what are you doing? Cu2 plus is going to make copper metal. That's a 2 plus charge, that's 0 charge, so add 2 electrons on the left. H plus, hydrogen gas is H2, so I need 2 of those, and I'm going to need to add 2 electrons also to that one, 2, 2. Which one is it? And then chlorine. Chloride becomes chlorine, and that means we need to have 2 chloride atoms or ions on the left, 1 chlorine molecule plus 2 electrons. And this one gets funky now because look at that. It's 1 oxygen atom with a 2 minus charge. Every man, woman, child and beast knows that oxygen is O2. So now we have 2 atoms of oxygen in 1 molecule of oxygen. That means we need to have 2 oxygen ions, each with a 2 minus charge. 2 times 2 minus is 4, so we need to add 4 electrons there. Now that's funky. Again, which one is it? Do we get chlorine or oxygen at the anode, and do we get copper or hydrogen at the cathode? The answer is this. At the cathode, you will see deposited copper. And at the anode, it depends. It's not an answer, is it? It depends. Because if the solution is concentrated, this is the A star territory, if it's concentrated, you get chlorine. If it's dilute, you get oxygen. So there are 2 possible answers of products at the anode. If it's a concentrated copper chloride solution, you will get the chlorine. If it's a dilute copper chloride solution, you would get oxygen. Okay, hydrogen. So why, you sat there thinking, well, why? Why copper? Why copper and not hydrogen at the cathode? Dead red cats. Because the copper is more easily reduced. Copper is more easily reduced. So it's easier for copper to gain those 2 electrons than it is for hydrogen to gain those 2 electrons. And at iGCSE, this will change if you do any post-16 qualification. At the cathode, this is a great thing to know. It's always hydrogen or copper. Because the only thing less reactive that they're going to use is copper, and that's on the syllabus and on the examiner's comments. At the cathode, it's always hydrogen or copper for aqueous. For aqueous ionic solids, it's either hydrogen or copper. So we've got this idea of competition in our heads. We've got cathode competition between the metal and the hydrogen, and anode competition between the halogen and the oxygen. So one of the ones that they said in your syllabus was concentrated sodium chloride aqueous. Why do we care about concentrated sodium chloride aqueous electrolysis. And it's concentrated. Doesn't work, well, it does work, but not for the products you want. Sodium chloride, aqueous. Small one, that's the cathode, dead red cats. That's the anode, that's positive, that's negative. We've got Na plus, and we have Cl minus. It's in water, so we also have H plus and O2 minus. So opposites attract. So to the cathode, we could get sodium, or we could get H plus. So cathode, that's where reduction happens at the cathode. Which one are we going to get? Well, if we got sodium being reduced at the cathode here, what would immediately happen would be the sodium would react with the water and it'd blow your face off because it makes some hydrogen. And what we do observe is not that. Our face remains intact and we actually get some hydrogen gas. What do I keep doing that? Go away. So we get some hydrogen gas. Where did hydrogen gas come from? Well, it must have come from the H plus. And there must have been two of them, and it's reduction. So it must have added a couple of electrons to make H2G. Oh, that's good. I like that. Okay, so at the cathode, we get hydrogen gas with concentrated aqueous sodium chloride, back to the purple. What do we get at the anode? Well, we could get oxygen, or we could get chlorine. But remember the previous slide, or the previous page? If it's concentrated, you get the halogen. So that's Cl minus. It's going to make Cl2G, gaseous chlorine. And that means there's 2 chlorine atoms there, and we need to have 2 electrons there. Oh, we're giggles, this is good. Well, we're almost good, because if you remember, one of the other products I mentioned on the previous page was OH minus, coming from the dissociation of water into H plus and OH minus. Deep chemistry, right? Go to the iGCSE. So if we remove, we'll ignore that one for now. The H plus has gone, it's gone to there. The Cl minus has gone to there. The only two things that are left are Na and OH. So from the electrolysis of concentrated aqueous sodium chloride, we also get NaOH. And you're like, well, whoopee-doo. What do we do with that? Well, hydrogen is used in the manufacture of plastics and is used in fuel cells. So industrially, that's important. Chlorine is used in, thank you, chlorine is used in disinfection and plastics and medicines. And sodium hydroxide is used in surfactants, detergent, cleaning agents. So industrially, the electrolysis of aqueous concentrated sodium chloride is very important because you get loads of crazy dollars for all this stuff. The other one we care about is, and you may have seen this in something called a Hoffman voltameter, is aqueous sulphuric acid. And the apparatus looks something like this. It's got 2 burettes. It's got some bungs on the bottom of here that normally leak and burn your fingers. And then it's got a couple of taps at the top there and a nozzle on there. Platinum electrode goes into here, and bubbles of gas go up here and collect and displace the water. And you find if you electrolyze water with a bit of acid in it, you get hydrogen and oxygen. Hydrogen will be at the negative cathode, oxygen will be at the positive cathode, H2 and O2, but the ratio is 2 hydrogen to 1 oxygen. This is how we found out the formula of water was H2O. Clever stuff, huh? Go chemistry. If we electrolyze dilute sulfuric acid, it's the same equation we've done a couple of times now. You need 2H plus and you need to add 2 electrons to make H2 gas. If you ever have a compound ion like SO4, which is sulfate, or CO3, which is carbonate, or NO3, which is nitrate, you don't get those given off. You don't get SO2 or CO2 or nitrogen oxides or NO2 or any of those things. What you always get when you have a compound ion is the product oxygen. And that's that funky one again, isn't it? 2O2 minus, that means, and we need to add 4 electrons. No, we don't. That's on the wrong side. Just teasing you. So we need to add 4 electrons to that side. So the electrolysis of sulfuric acid will give you hydrogen and oxygen, and also proves the formula of water as being H2O. Okay, so just looking down the syllabus, what else do you need to know? You need to know about the electroplating of copper. Electroplating. Copper. If you want to electroplate something, you want to take some cheap metal and coat it in an expensive metal, then you would do electroplating. This is how cheap jewelry is made. If you just do a gold coating or silver coating, and inside is steel or aluminium or something, and they can sell it and it looks beautiful, and then after a few weeks it rubs off and you were cheated. Anyway, on that bombshell, we can have another electrolytic cell. Here we go. Small one negative, big one positive. Hate cats, kill cats, reduction. That means that's the anode. Let's say at the anode, what happens at the anode? Well, oxidation happens at the anode, and reduction happens at the cathode. So if I want to plate something with copper, I'm going to need some copper ions, aren't I? Yes, Mr. Visually. So that's copper 2 plus. Let's put some copper 2 plus in there, and let's put I don't know, a fork. There you go. There's a fork. Forgive my terrible artistic skills. That's a fork. We'll put the fork at the cathode. So here's the fork, cathode. And that's going to pick up copper. We're going to get copper deposited, aren't we? And it's going to get a layer of copper solid on the outside of the fork. So make the fork out of something cheap like steel, make it part of an electrolytic cell. And you can do this with coins or, I don't know, the bathtub. And then you would also make the anode, you would make that out of copper. Why would you make that out of copper? Well, because if you kept taking out all the copper 2 plus, which as you remember is blue, from solution, and sticking it all over your fork, all the copper 2 plus will eventually go, and this will become clear. The solution will clear. But if at the anode you have a copper anode here, then that copper can oxidize and make copper 2 plus and 2 electrons. Oxidation is loss of electrons. Copper 2 plus, do that in blue. Yep, copper 2 plus. So the copper 2 plus that's taken out of the solution by the fork is replenished by the copper anode. Beautiful. And the last thing, is that the last thing? Yeah, the last thing, beautiful, on your syllabus is this. And this is a supplemental electrolysis of aluminium. Cool. So they often give you this as a drawing. I'm having to draw it, apologies for that. And you're thinking, what am I drawing? Well, I'm using black because this is made of carbon, and this is the carbon cathode, and these are made of carbon, you guessed it, these are the carbon anodes, and the iGCSE want you to know that aluminium oxide is mixed with something called cryolite. Okay, so cryolite is added in there. Why do we add cryolite? Is it just so I can make hilarious comments on YouTube? No, it's to lower the melting point. So it costs lower melting point. So costs less to make aluminium. Notice the pronunciation. Aluminium. Well done. So we've lowered the melting point, cryolites, so it costs us less crazy dollars to make our aluminium, which is really good because aluminium is used in aircraft, cars, that sort of thing. Lightweight, malleable, ductile, good conductor. How on earth do we get aluminium? But aluminium comes off here, pure aluminium, because aluminium oxide is Al2O3. And oxygen has a 2- charge, so 3 times 2- is -6, right? And that means if that's 0 overall, so minus 6 plus 2x equals 0, that means x must equal plus 3. So the charge on aluminium is plus 3. So the reduction must be Al3 plus 3 electrons goes to aluminium. And that's great. I can build an aeroplane. Whee! And then oxygen, that funky little oxygen 1, 2O2 minus goes to O2 plus 4 electrons. And that's great because we'll make some oxygen. What am I going to do with the oxygen? Well, these electrodes are made of carbon. And the carbon reacts with the oxygen and it makes CO2. And you're like, great, greenhouse gas, woohoo! Well, yeah, and yeah, because you could just vent this to the atmosphere, and I'm sure in the olden days that's what they used to do. But now they often cite a soda bottling plant next to the aluminium smelting works that'll turn you onto your Coca-Cola, and make a solution of carbonic acid, which is H2CO3, which is fizzy soda. So the CO2 is used by the bottling plant next door. So aluminium, make my aircraft. CO2, make my Fanta, Coke, other drinks are available. And that's uses of industrial uses of electrolysis. Number 1 was electrolysis of aluminium. Number 2 was electroplating of copper. This is just information, sulphuric acid. It's not used industrially, it's just funky and fun to do. Concentrated sodium chloride is used industrially because of the chlorine, the hydrogen, and the sodium hydroxide. And this is the electrolysis of ionic salts and molten salts. Okay, I hope you found that useful and as fun as I did. Enjoy the rest.